Oliver. Wade Oliver has over a decade of research and applied experience focusing on the characterization of groundwater systems. He has managed over 100 projects involving evaluations of aquifer recharge, groundwater surface water interaction, inter-aquifer flow, and future groundwater conditions and availability for local and regional groundwater management entities in Texas. He currently manages Intera's Houston office, so please join me in welcoming Mr. Wade Oliver.
Well, good morning, everybody. I really appreciate the opportunity to be here with you today and to see you. I hope everyone's staying warm here. It's a bit of a challenge, but that's okay. So it's always a pleasure to come to the symposium and really appreciate you asking me to attend. So my talk today is on modeling of the High Plains aquifer systems. That includes the Ogallala, includes some other aquifers, and we'll get into that. But as Brittany said in the introduction, I'm Wade Oliver. I'm a hydrogeologist and groundwater modeler. So that's my background here. So I'm gonna start at an obnoxiously high level, okay? And that's what is a model? And I don't just mean a groundwater model or even a computer model. I mean, just in very general terms, what is a model? It's a simplification of reality. So yes, this applies to computer models of groundwater flow, which is what I do, but it also applies to little model cars. It applies to more abstract things like mental models of how you see the world. It's just a simplification of reality. And I'm confident that not one person in this room asked for or is particularly interested in a hydrogeologist coming up here and getting philosophical about something, but I'm going to do that anyway. It's for selfish reasons, and you'll see that here for a second. So here's an example of a mental model that I hold, and that is this: that how much attention, focus, energy that you give to a subject, whatever that subject is, that drives how interested you are in that subject. Okay, so I'm going to say it again. How much attention you give, how much energy you give, drives how your feelings, how interested you are in that subject. That's the reverse of what I would guess is the common knowledge view, that how interested you are drives how much effort you give to something. Okay, so that's my proposed mental model here. And as by way of example, I went to A&M. I'm sure there's probably at least a couple Aggies here in the room. I knew that was coming. And I started in mechanical engineering. I didn't start in geology, and I was not enjoying myself freshman year there in mechanical engineering. I'm like, if I stay in engineering, I'm going to be stuck behind a desk staring at a computer screen for the rest of my life. Okay, I've got to get out. So I'm going to go to geology. I'll be getting dirty all the time. I'll be climbing mountains. That's what I'm going to be doing. Fast forward some not small number of years, and guess what I do for a living? I sit behind a desk in front of a computer screen, and but I'm not bitter about that. I actually enjoy it because I had invested a lot of time and energy and effort grad school. Got really interested in this stuff, and so my interest in that came out of the effort, not the reverse. Okay, so there's my philosophical moment here, and I bring this up. I mentioned this was for selfish reasons because I'm up here to talk about the hydrogeology of the Ogallala Aquifer and the development of and use of computer models for aquifers, okay? So to put that in very, very plain terms, I'm here to talk about computer modeling of wet dirt to a group of people that probably are not inherently interested in this. And I bring this up to say, yes, you can be interested in it if you give it enough effort, Number one. And number two, if you're not interested in it, it's your fault, not mine. So I think this is worth your energy to learn about. The High Plains Aquifer system. Not most of you, I think, live up in this area, not all of you, but it's important for a lot of reasons. Well, it's an important aquifer system, and I'll touch on that. It is a very different aquifer system than the others in the state, which I'll touch on, and for those reasons, I think it's worth your understanding. So these are maps of the major and minor aquifers in the state. The majors are on the left, minors are on the right. So up here in the Panhandle, we've got the Ogallala in blue. On the left side, that's really the major aquifer up here. Water Development Board defines a major as an aquifer that provides a large amount of water over a large area. So this qualifies. On the minors on the right, you'll see several. The Rita Blanca is in green. It's kind of hard to see on this screen, but it's in the upper northwestern portion of the Panhandle. Then there's the purple Dockham aquifer. If you're not familiar with the term Dockham, you're probably familiar with Santa Rosa. So the Santa Rosa is the productive portion within the Dockham aquifer. So that's the purple, both the hashed and then the solid color. The solid color is where it's exposed at land surface. The hash is where it underlies another aquifer. And the Blaine, kind of in the eastern portion of the Panhandle, that's Permian age. Not really going to focus on that. But this is, so a couple of you might have seen me talk about this slide before, but this is a stratigraphic column showing the different aquifers that I just mentioned. Ogallala, that's on the order of a few million years old. The Rita Blanca, Jurassic age, is a big gap in time here. We're talking about something 150 to 200 million years old. And then the Triassic Dockham, we're talking about something 200 to 250 million years old, okay? So you probably stopped listening to me and started looking at the video on the right. And I show this on the heels of what Dr. Mace presented earlier, okay? He talked about all the geologic changes over time in this area. And so this video, these types of maps are called paleogeographic maps, so what the Earth looked like at different points in time. So the bottom left, you can see the number of years ago that each image was, it's not taken, but developed. And so you can see that in this area of the world, the map centered on the United States, there have been some substantial changes over the last 500 million years. To a geologist, and I know there's a few in the room, a few million years is not any time at all. This is over hundreds of millions of years. But it is really these changes that drive the geologic makeup, the hydrogeologic makeup of what we now consider the water resources here. I want to highlight, so Dr. Mace highlighted the Ogallala deposition. I'm going to highlight the Dockham deposition here for a second. So at the Triassic period, one of those images in what I just sent, or what I just showed, this is what the High Plains, what the structure was. Most of the High Plains was covered by what was a shallow inland lake, okay? And so rivers are flowing towards the lake. They're depositing sediments in deltas in the same way that sediments deposit today. So the larger grain sediments depositing right as it enters the lake, smaller grain sediments farther in. And so you've got this big inland lake. We can see the evidence of that in the way the Dockham is structured today. So this is a northwest to southeast cross section of the Dockham. To give you, we're separating the upper Dockham from the lower, and then you can see the sandstone running along the entire lower extent of the Dockham. That's the Santa Rosa. But what's unique about this is that the Dockham is an outcrop to the west in New Mexico. It is also an outcrop to the east of the High Plains, and you saw that on the Aquifer map. And so it's just this big bowl that underlies the whole thing. And so that's a feature of the geologic past that led to this big bowl-shaped character of the Dakum. Also, for those of you that drill wells are familiar with it, when you run into the thing called the red beds, that's the upper section of the Dakum, okay? I have the privilege of working with Groundwater Management Area 1 and the districts in Groundwater Management Area 1 in the northern portion of the Panhandle, helping them develop what are called desired future conditions. As part of this process, we work through a whole lot of the geologic characteristics and hydrogeologic characteristics of the aquifers. We had a really cool opportunity to have our last meeting in Paladuro Canyon State Park, okay? Now, I'm sure most of you have been there, but for a hydrogeologist that gets interested in this kind of stuff, it was neat because I think it's the only place in the state where you can have a meeting about aquifers, the Ogallala and the Dakum in particular, and look out the window. This is the MacDick Pavilion on the left. Look out the window and see the rock formations that make up those aquifers. So it was a really cool setup. So if you haven't been to Paladuro before, or, I mean, it's 30 minutes south of here, or you haven't been in a while and you want to look at it from that point of view, I encourage you to do it. I thought it was a really great setup. So getting back to this, the takeaways that I want you to take from my talk are the Ogallala is important, it's different, and it's worth investigating for yourself. To highlight this, so we've got the majors map again on the left, major aquifers. On the right, this is a map many of you may have seen before, but it's historical water level declines for all the aquifers in the state, okay? So I haven't put numbers to it, just know that the warmer colors, the reds, the oranges, those are larger declines. Okay, the cooler colors, the light blues, those are smaller declines. So you can see in the Ogallala and the Panhandle, there are declines, without a doubt, but they're not enormous. The Trinity is the aquifer with the biggest declines, running from central Texas up through the Dallas-Fort Worth area. They have had over, in some places, 1,000 feet of water level decline historically, just enormous declines. And so if you look at this map on its own, you may be tempted to think, my gosh, they are using a ton of water. They need to cut that out. They're clearly using more than we are here in the Ogallala. That is not the case. So I had too much fun developing this figure. I'm not sure if it's of any interest to you, but that's neither here nor there. I have scaled the area of each of these aquifers to how much pumping actually comes out of these aquifers, okay? So these are all those 9 major aquifers in the state. You might notice that the Ogallala is quite a bit bigger than the rest of them, okay? I've put the actual amount in terms of average pumping from 2015 to 2017 there. So the Ogallala's 4 to 5 million acre feet per year of production. The next largest, the Gulf Coast aquifer, is 700,000, so less than a quarter of the production out of that aquifer, and it goes down from there. The Trinity, the one in green, kind of the fourth one from the right, that's the one with 1,000 feet of drawdown, okay? So they're using less than 200,000 acre feet per year, and they've got 10 times the drawdown of the Ogallala. I hope that tells you that these are very different systems. As a hydrogeologist, I will tell you they are very different systems. Highlight another aspect of this, and the fact that the Ogallala is different. This is a plot showing on the x-axis there's storage volume, estimated storage volume in the aquifer, moving along the x side to side. Moving up and down is the estimated 2016 production from each aquifer, and I've included both majors and minors on this plot. So you see where the Ogallala is? It's kind of off by itself, okay? It has a very high amount of production, and it's on the left side of the plot, and so it has a very low, comparatively, volume and storage, okay? the amount of water that's used out of the Ogallala is not really a function historically or been limited by how much is in the aquifer. It's the amount that people are using it is being driven by other factors. So that's one of the reasons we model, and so I'm going to get into this. This is the Ogallala and the Dockham, so those are two high plains aquifers compared to the Trinity, which is the green one that I mentioned, and the Edwards, so that's the karst aquifer running through the hill country. And these are some of the key characteristics that drive whether an aquifer gets really highly utilized or whether it doesn't, okay? It's not just storage volume, it's not just the footprint, aerial footprint. Ogallala is an unconfined aquifer, okay? The rest of these are either confined like the Dockham or have confined and unconfined sections. I'll touch on what that means in a minute. Lithology matters a great deal. What are the rocks? You know, Dr. Mays mentioned the rocks coming down from the Rockies. Having sands and gravels, water is able to flow through the aquifer much better through that than it is through compacted clays, okay? That matters a lot. That ties into permeability, or if you've heard of hydraulic conductivity or transmissivity, those are just a description, the hydrogeologic characteristics of how easily water can flow. Primary or secondary porosity, that's just whether water's flowing through in between grains of sand and gravel or whether it's flowing through cracks or dissolved out sections like the Edwards. Now, water quality, you know, is it something that you can use? Available drawdown, whether recharge comes in, that matters a great deal. And then storage volume. So all of these come together to determine whether an aquifer is useful, okay? It's not just recharge, it's not just storage volume, it's not just transmissivity, it's all of them together. And that's really one of the main reasons why we model, and it's one of the main reasons why you can see these vast differences between the Ogallala and the Dockham, which are sitting right on top of each other. The Dockham's got more water in it than the Ogallala, but they're used very differently. Does that make sense so far? Okay. I mentioned that I would talk about unconfined versus confined, just very briefly. Unconfined is typically an aquifer that's shallow, and when you drill a well, the water level you measure in the well is the same as what you see in the aquifer. If you go to a confined aquifer, there's a confining layer, typically a clay on top of it, and the water level that you measure in a well usually rises above the top of that aquifer, okay? That matters because of how the aquifers respond to pumping. The Dockham, as a confined aquifer, is going to have much larger drawdowns that go a lot farther because it is a confined aquifer than the Ogallala. So all of those characteristics that I just described, they kind of fall into what I think of as the conceptual model of an aquifer. This is, how does this work? How do we think this all works together? And then we move it over into what's called a numerical model, a computer model, and we try to fit it all together and say, you know, these are all complicated, they all interplay. And so we take the numerical model, we calibrate it, and then we can use that to make predictions or answer what-if questions. If we pump this, these are going to be the impacts. If we manage it in a different way, these are going to be the impacts. And that's the process that we're doing with Groundwater Management Area 1 right now. And that's honestly, that is not any different than any other modeling process. So my kind of goofy mental model at the beginning of the talk still follows the same process. Collecting data and observing how things work. My experience at A&M, building a model. Oh, I think it's because I'm fine sitting behind a computer all day because I'm actually interested in this because I've invested a lot. That's my mental model, and then you use that to say, how else can I apply this? Okay, that's that same modeling process, just in a different context. So to briefly take you through a few things about the model. This is the model area on the left side here. So we've incorporated some, like the Pecos Valley Aquifer in the south, a lot of the underlying aquifers like the Dockham into the numerical model. This comes on the heels. The Ogallala is one of the most researched aquifers in the country, or probably is the most researched aquifers in the country. There have been other models, but they were all developed for different purposes, had different footprints. This is bringing a lot of that together, bringing in the most recent data so that it is most useful for the way that people are making decisions about the Ogallala today. The High Plains, as Dr. Mace mentioned, is relatively flat, but it is tilted. Rivers do flow from west to east because they recognize gravity. So you've got a substantial amount of elevation decline as you move from west to east. The thickness of the Ogallala is not constant everywhere. So you can see in the northern portion, you've got areas that are as thick as 900 feet in some areas. You get into the southern portion, it's commonly less than 100 feet thick. So I know it's tempting to think of it all as the same, but it is very much not the same depending on where you are, and that can change even over short distances. To dig into that, no pun intended, a little bit. So this is a cross section from geophysical logs that were used as part of this modeling effort. So a geophysical log is just a tool. It's put down a well. You're evaluating the geologic characteristics of the aquifer as you go down. So that's what the squiggly lines are. The colors represent our interpreted lithology. So is it a sand? Is it a clay? Is it a limestone? Okay. The limestone's all below the dock, and we're not really focused on it, but you can see in the area interpreted as Ogallala that it's a very sandy, in fact, sands and gravels there. Then you can see where you hit the red beds, and that at the base of the Dockham, you pick back up that Santa Rosa again. Okay, so you can see all this in the logs. This is related to the model, but it's actually from some work that we did for GMA1. I've plotted all the well depths in the upper or in the panhandle here in GMA1. The reddish colors are shallow wells, and then the bluish colors are the deeper wells up to 600 or 700 feet or more. Okay, you can see this is not very evenly distributed. So this ties into the thickness changes in the aquifer that I referred to earlier. There are patches where you've got lots of really deep wells, and that's, you got a question? Yes. These are all water wells, that's right. Yes, yeah. They're not oil wells and they're not monitoring wells, they're production water wells, yeah. So this is, you can see how it's not evenly distributed. In fact, the next map makes that point. I think this map moved a little bit. That's okay. Same footprint as before. The reds, these are well yields, okay? So the reds represent low well yields, 20 gallons per minute or less. The blues represent 400 gallons per minute all the way up to 1,000 gallons per minute or more. Do you see kind of a spatial difference in what's happening on this figure? Okay, you've got really high well yields in the northwest. You've got moderate, this like teal color on the eastern section of the panhandle, and then around the city here, you've got a bunch of highly clustered, low yield domestic wells. Okay, and so yield is driven by two factors. It's driven hydrogeologically by how much the aquifer can provide, and it's driven on the human level by what people actually need the water for. You're not going to put in a 1,000 gallon per minute well for your house. Okay, so those two factors together are driving this distribution of well yields throughout. So we're taking all this. Yes, sir. So yeah, I mean those wells, along with everyone else's wells, go into the Water Development Board databases, and so they're plotted here. Yes, yeah. So all of that conceptual model material goes into the numerical model. I'm not going to inflict too much pain about what it takes to develop a numerical model, except to say that we're capturing all of those conceptual model elements in a mathematical program that includes the physics of groundwater flow so that we can test those what-if scenarios. And so it includes flow between aquifers, includes recharge from playas or in outcrop areas, includes irrigation return flow, so flow from irrigation back to the aquifer. It includes interaction with streams, pumping, all of those things. And we calibrate those to lots of things, but primarily water levels. So the right side of this is water level well locations, target locations. And the left side of this is it's called a cross plot, but the x-axis are measured or observed water levels, and the y-axis is those water levels simulated at that well at that time in the model, okay? So if a dot falls directly on the line, that means the model matched it perfectly, okay? Now, not every dot falls exactly on the line, but I would say that our dots are pretty darn close to that line. Okay, so we use this to have confidence that when we employ predictions, when we're using the model to make forward predictions, help us make management decisions, that it is going to give us reliable results. So I think if in any way my presentation has piqued your interest in groundwater, then I'm super excited. I've included a couple or a few useful resources here. There's two pretty substantial reports for the High Plains GAM, Groundwater Availability Model, that you can get on the Water Development Board website. Groundwater Management Area 1 is going through the joint planning process right now, and there's a panhandlewater.org. You can access both the regional planning process and the joint planning, the desired future condition process there. So all the presentations go up there after every meeting. And then I have to plug it's like a 100-page text from the USGS called Basic Groundwater Hydrology. Heath, 1983, there's the link. That is the most accessible basic introduction to groundwater hydrogeology that I know of. And so if you're interested in learning more, that's a good resource for you. So with that, do you have any questions? This is my dog with questions. And
I have a question.
Yes, ma'am.
What's your dog's name?
My dog's name is Peanut.
Peanut.
Yeah, and she is the love of my wife's life. Okay. That's right. Okay.
Which is, in my mind, I grew up in Moore County. They're all decreasing in Moore County. Why are our wells, or some of our wells, increasing in Moore County, in the Ogallala?
So that's a great question, and it's a bit dangerous for me to answer because I haven't seen the document that's in front of you. But the water usage in Hemphill County is different than a lot of areas to your west, and that's exemplified by your current set of desired future conditions that we're evaluating for 80% remaining after 50 years as opposed to 50% or 40%. So the use is different there. It's not out of the question that there are localized recharge events that are occurring that's leading to that uptick, but I'd need to look into it in more detail before I say something to a group of 200 people. Yeah. Yes, Steve. Let me. I missed the first part of your question. What would you do to update this to better consider water quality? Okay. So we're not, to be clear, the current High Plains GAM does not explicitly model water quality. There is a way to do that, but that's typically more for environmental applications. The way that you can track it within a model like this is to do essentially the modeled age dating of water to see if we're matching water quality changes that are tied to changes in groundwater age. That's how I would do that. But certainly part of the conceptual model for this is to evaluate areas with different water quality using both lab results from wells, and then there's a lot of geophysical techniques for evaluating water quality where you don't have lab samples to be able to evaluate that, not from a numerical model standpoint, but from a characterization standpoint. Okay.
Okay, so I appreciated your slide saying predictions and then what if.
Yes, sir.
I think from my perspective as a modeler that I don't consider models predictive pretty much ever. They're comparative, so I liked your what if part of it, and I would put the emphasis on that. So if I have this set of scenarios and I run them against this is the likely difference between those two things, as opposed to if I put these inputs in, this is what I'm going to have in 50 years. That's fairly speculative, and it depends on a lot of things that we don't know. So for instance, the gentleman that was asking about the wells in Moore County, and part of that has to do with well hysteresis and rebound. So if you turn off a well and leave it off for a while, water levels are going to come back up. That is not from recharge, generally speaking. It can be, but for the most part for the Ogallala, it's not from recharge. It's from the fact that water is able to flow laterally to come back to that well, following the northeast to southwest gradient that's typical.
So it's a great point, and I appreciate you bringing that up. So part of my hesitation on the answer was, is this localized wells going up, or is everyone's wells going up? And that would be the difference. But certainly recharge takes a long time. More people typically.
And so Moore County's got the Canadian River running through it, and so
right.
There are some issues that are related to that as well. So you're right. I think the biggest thing you said was that it's complicated, and it takes more than just a quick answer.
That's right.
But again, it goes back to if you do this, what happens compared to if you do that, not what is the future going to be for sure, because we don't know that. The first job I was offered was to do groundwater modeling for 10,000 years, and I turned that one down.
So I appreciate you making that point, and I actually share your view on that, which is why I predict the only word in there in quotes on that slide there, because we're not typically making predictions, just as you said. We're answering what if questions. If a certain path were to go forward, what are the likely impacts or types of impacts to the aquifer under that condition? Any other questions? Yes, sir. So it's a good question, and it's interesting that the question. Okay, I will attempt to repeat the question. Your question, as I heard it, was, will the Ogallala flowing from west to east? Will it eventually just vacate the west and be concentrated in the east over the next 100 years? Is that the nuts and bolts of it? So the short answer is I doubt it. That's not, groundwater does not flow super fast, even underground. Okay. Now, might there be an element to the west going dry more quickly than the east? That is possible. That's something that we can evaluate with models. I would say that there is also, if you remember the yield maps and some of the production stuff that I showed, there's also more use in the northwestern portion of the panhandle than there is in the east. So it would be hard to parse out whether that's a gravity thing or whether that's just because people are using a whole lot more.
join me in thanking